Of the of alpha. So let me to focus on this quantity because this is a partition function, as I told you. Sorry, better. I want to make a factor here from the beta, so just write this expression. There is a nice way to pass from the energy to Hamiltonian. In quantum mechanics, you know that if you have Hamiltonian, you can find the energy. No? Energy is the average of Hamiltonian, I don't want to use the quantum mechanics, just I want to tell you that this looks like the average of the some quantity, this, minus beta Hamiltonian, plus something here. And this NS can be the average of the something like Hamiltonian, we can call it N. Because in thermodynamics, you have a several combination of Hamiltonian with the different things, like Gibbs energy, like so this is the Gibbs energy. H minus mu n is called Gibbs energy. So just I say that the NS can be the average of something, we call it N, and E R is averaged to the something like Hamiltonian. And from thermodynamics, immediately I know that what is here. From thermodynamics, I know that this is H minus mu n. So I guess that alpha over beta will be minus mu. And alpha will be minus mu beta. So I need to still to check because alpha is minus, no, sorry. So make a factor from beta, so beta is beta. So beta, alpha over beta NS. Alpha over beta NS minus mu. Yes, that's true. And alpha will be minus mu over k. Yes, because I checked in my notes, it's written minus mu over kbt, and okay, minus mu over kbt. So, but this is not the only way. This is very handy, you know, very, very handy. I just by the hand, I find that there is another method to understand the meaning of this, and that's enough. So we have the alpha, so you can bat and a little bit write in the better form this. Alpha minus mu beta minus mu. Sigma r and s, E minus beta, E r minus mu and s. Okay. Okay, this is not the only way you can understand the role of the alpha. So alpha is proportional to the chemical energy. So when I talk about chemical energy, I need to mention here that the chemical energy is something like pressure, and it's something like the T. If you have two systems, they are in the thermal connection to each other, as long as there is no transport of the energy, they have the same temperature. As long as they don't have any transport of energy. Energy means thermal energy. Exactly thermal energy, Q. Okay? Delta Q0 means that they have the same temperature. As long as they have the same volume, as long as you keep the volume of the two systems constant, so you have a, you can say that about the, you can talk about hydrostatic equilibrium. Hydrostatic equilibrium is the one, the word which they generally they use. For me, it's just you balance the pressure, hydrostatic. And what about that? You learn here that, yeah. Delta Gibbs, I think. I have to be very careful when I write some of the. Okay, they didn't write anything here, so this is called a chemical equilibrium actually. I think that Gibbs will be 0, but we need to check it then. Gibbs. That's all. In each thermodynamic system, at the same time you have one of them, or you can have all of them together. All of them means together the system is completely neutral. So no particle transportation, no change in the volume, and no change in the heat. That means that two systems is dead already, or freeze. Completely freezing. If you freeze two systems in the contact to each other, all they could be happen together. No, but if you freeze the system, but not very much freeze it, I mean you give this possibility to the system to transport a little bit heat between each other, so you can have the thermal equilibrium. So this is a thermal equilibrium. Name is very important because this is called a thermal equilibrium. Chemical equilibrium, this is called a hydrostatic. And this is happening in the life body also. Of course, you know, using the statistical physics for the human body or animal is not very correct. But I mean, what in the medicine they use the pressure is this hydrostatic pressure of the blood, yeah, in the body. It's exactly like that, you know. When the thickness of the special parts of the body, you know, change it, so they can read it. They can detect it that the pressure of this change. For chemical equilibrium also. So this is very for example, even in the decay of the proton, for example, to the neutron and electron and neutrino, you can